Okay, question 4 here is on the photoelectric effect. The first question, explain why photoelectrons are not emitted from the metal surface unless the frequency of incident light exceeds a minimum value. Well, the light is made of photons. With energy HF. And there's a minimum energy required to release an electron. And if there's a minimum energy required, then there must be a minimum frequency required. So there's a minimum HF, therefore min frequency. Okay, then you're given the graph of the results. We'll come back to that graph in a second. Use the graph to identify the minimum value of the frequency for photoelectrons to be emitted. Well, this is a reasonably easy one because this is Emax, this is their kinetic energy. And if they're not going to be emitted, they're going to have zero kinetic energy. So we're just going to continue this line back down here to the axis and see where that intercepts. It looks like it intercepts at about, that would be 0.9 there, so about 0.93, something like that. So 0.93, and remember to look at your units, that's times 10 to the 15. So that equals 9.3 times 10 to the 14 hertz. Okay, determine the Planck constant. Well, the equation for the line is Emax equals HF minus phi. That's in your data booklet, where phi is the work function. That in the format y equals mx plus c gives us the gradient being Planck's constant, because the x-axis is f and the y-axis is Emax. So the gradient is Planck's constant, so h equals the gradient. We need to then find the gradient of the graph. Well, if we go down from here, then we get whatever that is, 1.5, 1.75, 1.8. 1.8 down here to whatever we just said that was, 0.93. And then across here we get about there, which is just over 3.4. 3.4. And then that one's 0. So the change in y is 3.4 electron volts. The change in x is 1.8 minus 0.93, which is 0.87, times 10 to the 15, remember. So the gradient must equal the change in y over the change in x. So 3.4 divided by 0.87 times 10 to the 15, which gives us 3.91 times 10 to the minus 15. Okay, so if the gradient is 3.91 times 10 to the minus 15, that must be h, but that, remember, because we've taken the units from the axes, that's in electron volt seconds. Planck's constant is normally given in joule seconds, so we just need to multiply that by 1.6 times 10 to the minus 19, and that'll give us joule seconds, which is 6.25 times 10 to the minus 34. And we know a value from Planck's constant is in the data booklet, 6.63 times 10 to the minus 34, so that's about right. So we're happy with that, and that's joule seconds. Okay, calculate the work function for the metal surface. Well, going back to our equation, the work function there is the y-intercept. So we can go back to our graph. Let's do it in a different color. We can go back to the graph and do a y-intercept there, which is somewhere around 3.6, between 3.7 and 3.8. Let's call it 3.7 minus 3.7 electron volts. And remember that this is plus C and this is minus, so we need to do the negative of that to get the actual value for the work function. So the work function equals the negative y-intercept, which is 3.7 electron volts. Now the Mark scheme will let you be a little bit more vague than that. They will allow you somewhere between 3.6 and 3.8. Okay, finally, the student repeats the experiment with a different metal surface that has a smaller value for the work function. Draw a line to show what the line would be. So I'll use another different color, let's say green. If we go back to our equation, yet again, we've got, this time we've got a smaller value for the work function here. The gradient is going to be the same because the gradient is still Planck's constant. So the only difference here is we've got a smaller value for the work function. And so what that is going to mean is that it's going to be a smaller numerical value. The magnitude is going to be smaller, but with the same gradient. So we're going to be going up something like that. Anywhere above the pink line, but having the y-intercept below 0 is fine. And the second mark is for it being parallel to that of the first line. And that's it.